Nos acompañan en la mesa principal el doctor Enrique Forero, presidente de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales, el doctor Jaime Rodríguez Lara, expresidente de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales, el doctor José Lozano, secretario general de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales, la doctora Margarita Perea, miembro número de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales, la doctora Elizabeth Castañeda, miembro de Junta Directiva de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales, y como invitada especial la doctora Ana María Rey. A continuación, tendremos el acto solemne. La Academia reconocerá a los dos científicos galardonados con el Premio Nobel de Física del año 2012, doctores Serge Haroche y doctor David Weiland, exaltándolos a la categoría de miembros honorarios de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales. Esta ceremonia tendrá el siguiente orden. Primero, palabras del doctor Enrique Forero, presidente de la Academia. Segundo, lectura y entrega del diploma e imposición de las insignias de la Academia al doctor Serge Haroche. Tercero, lectura y entrega del diploma e imposición de las insignias de la Academia al doctor David Weiland. Palabras de los nuevos miembros honorarios y en este momento doy la palabra al doctor Enrique Forero. Gracias, doctor Forero.
Gracias. Señores miembros de la Junta Directiva de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales, doctora Margarita Perea, doctora Ana María Rey, estimados conferencistas invitados, profesores, estudiantes, señoras y señores, members of the Executive Board of the Academy, Dr. Margarita Perea, Dr. Ana María Rey, dear invited speakers, professors and students present, ladies and gentlemen. La Academia Colombiana de Ciencias Exactas, Físicas y Naturales eligió en su sesión del pasado 10 de junio a los doctores Serge Haroche y David Weiland como miembros honorarios, el más alto honor que otorga la Academia. El doctor Serge Haroche, como sabemos, trabaja en el Collège de France y en la Escuela Normal Superior de París. El doctor David Weiland trabaja en el Instituto Nacional de Estándares y Tecnología y en la Universidad de Colorado en la ciudad de Boulder, Estados Unidos. Los doctores Haroche y Weiland compartieron el Premio Nobel de Física en el año 2012. La Academia se siente muy honrada al recibir hoy como nuevos miembros a dos ganadores del Premio Nobel. The Colombian Academy of Exact Physical and Natural Sciences elected Dr. Serge Haroche and Dr. David Weiland as honorary members at its regular meeting held on June 10, 2015. This is the highest recognition, the Academy's highest recognition. Dr. Serge Haroche, as we know, works for the Collège de France and the École Normale Supérieure in Paris. Dr. David Weiland works for the National Institute of Standards and Technology and the University of Colorado in the city of Boulder, United States of America. Dr. Haroche and Dr. Weiland shared the Nobel Prize in Physics in 2012. The Academy is extremely honored to welcome two Nobel Prize winners as its new members. Voy a leer el texto del diploma. Academia Colombiana de Ciencias Exactas, Físicas y Naturales. La Academia, atendiendo a la ilustración, méritos, aportes científicos y demás circunstancias recomendables que distinguen al profesor Dr. Serge Haroche, ha tenido a bien elegirlo en la sesión verificada el día 10 de junio de 2015, miembro honorario, y para que conste se le expide este diploma firmado por el presidente, refrendado por el secretario y autorizado con el sello de la Academia, dado en Bogotá a los 16 días del mes de junio de 2015, Enrique Forero, presidente, José Lozano, secretario. The diploma basically says the Colombian Academy of Exact Physical and Natural Sciences, taking into consideration the knowledge, the merits, the relevant contributions to science, and other circumstances, has elected Professor Dr. Serge Haroche as honorary member. The diploma is signed by the President and the Secretary of the Academy and is dated at the 16th day of the month of June of 2015. Invito a la al doctor Haroche a que suba al estrado, por favor. Invito a la doctora Margarita Perea para que imponga las insignias de la Academia al doctor Haroche. I invite Dr. Wangland to please come to the fore. And I ask Dr. Ana Maria Rey to please come and, okay, give him the diploma first. The pin, then the pin.
I'll work on it later.
If you want to say a few words, you're welcome to.
First, I'd like to thank Enrique for, first of all, organizing this meeting here. It's my first time in Colombia, and it's been very nice to be here, and I've had the chance to meet a few of the faculty and students, and I'm very impressed with the work and the enthusiasm. Of course, I'm very honored to receive this award, and I very much appreciate the Academy and being invited here and enjoying this meeting. So thank you all for coming, and thank you.
Gracias. I am ashamed it's the only word I can say in Spanish, but I really want to thank you for this great honor. I'm deeply moved to have been named a member of this of your academy. I know that the mission of the Academy of Colombia is to try to promote basic science and culture in Colombia, and to try to convince the society and the government that research, curiosity-driven research, and cultural values are essential for your country. We share the same values in France. You mentioned that I was a member of the Collège de France. It's an institution which was founded in 1530 at the time where I think Colombia was populated by native people, and it was at the time where the first Spanish people came to this country. At that time, the Collège de France was founded to defend the values of science and culture, and this institution has gone through the centuries, through the different political regimes, and kept the same values, which I think we share with the Colombian Academy. And I am also very pleased to share this recognition with Dave Wineland, and I am sure that, as he said, that this will help promoting the collaboration between Colombian scientists and scientists in France and United States and other countries. And we would really welcome students, postdocs, and colleagues to visit us, and we'll be very happy to come back to Colombia in the future. Thank you very much.
Bueno, mientras terminamos este acto protocolario, quiero invitar para que se vayan alistando, por favor, los doctores Alain Aspet, el doctor Boris Rodríguez, el doctor Pablo Guimaraes y el doctor Serge Haroche. Muchas gracias. Bueno, el doctor Haroche puede quedarse en la mesa, por favor. Y el doctor Alain Aspet, por favor, nos acompaña, el doctor Boris Rodríguez, Pablo Guimaraes. Y vamos a abrir en este momento el panel de discusión, el cual será moderado por el doctor Jean-Pierre Galop. Doctor Galop, por favor.
We
This is a strange situation for me because I have no experience of this kind of thing.
I need to have a connection to the
La cosa es que este momento debe ser un momento de discusión y de gran libertad de expresión de tanto de las personas que se han invitado aquí al panel de discusión como del público, que no se siente que si algo le pasa por la cabeza de preguntar una pregunta, pues que lo hacen, que toman un intento de introducir un tema de discusión. El tema, por supuesto, principal, bueno, lo digo en español, lo puedo decir primero en español, se refiere a la naturaleza del fotón y de la luz en nuestro cómo está. Todo fue uno de los temas principales de las presentaciones de hoy en día, ¿no? But to introduce this discussion, Professor Aspe suggests to me he has prepared for another event in France at the beginning.
Was the world, it was the first day of the International Year of Light in UNESCO in Paris. So it was just for this launching of the Year of Light, and I had a small presentation about light.
That was for a mondial event?
Well, yes, it was the International Year of Light.
Yes, sure. Of course. And then we have the pleasure to have a repetition of this presentation he gave at this occasion.
Provided that the technique works.
Yes, of course the technique will work.
They are surprised.
Everything works here in Colombia.
Is it done? Yes, it's working. Should be on. Of the International Year of Light is the fact that light has always been at the heart of quantum revolutions. And there is no, yeah, okay. And so let us, okay. So it will be 3 parts, and it will not be long. It was strictly 15 minutes at the UNESCO, so probably it will be about the same. First, the beginning of quantum physics, from Planck and Einstein to the lasers, and then from the Bohr-Einstein debate to quantum technologies, and a little bit of elaboration of what we are living today. So you all know that quantum mechanics started when Planck introduced the hypothesis that the exchange of energy between matter and light is quantized, and then 5 years later, Einstein made a much more revolutionary hypothesis that light, not only the exchange of light and matter are quantized, but light itself is made of light, is made of least quantum, of quanta of light. Then I like to emphasize on the fact that as early as 1909, before Bohr's atom, Einstein was obsessed by the equation. But on the one hand, there is this hypothesis that light is a quantum. On the other hand, he knew about the work of Young, Fresnel, and Maxwell, and all the other people. And so by some wonderful reasoning, and this paper can be found on the web, he showed that light has to be considered both as a wave and a particle. So wave-particle duality was already there. Well, I have no time to elaborate on that. Let me continue. If you want, I can do in more details, but it would be too long. Then Bohr in 1913, as we say, not only quantized the motion of electron, but also he says that when electron jumps from one state to another state, then light is emitted, and what is, how do you know the frequency of light? The frequency of the line by the relation h nu equals the difference between levels. Then de Broglie introduces the reciprocal of the idea of wave-particle duality for light. Now de Broglie introduces the idea of wave-particle duality for material particles, such as electrons. And, well, okay, this is what Serge has already shown. It is this experiment done by Jean-François Roch and his team at École Normale de Cachan, in which you create a single photon here. Then the single photon is sent on what is called the Fresnel biprism, okay? And if you have a single photon going on the Fresnel biprism, it can either go up and be deflected down and detected by that detector, or go down and be detected up by the other detector. And you prove that you have a single and only one photon by looking at the coincidence between detection here and there, and you find that the coincidence is 0. There is only one particle going either up or down, and if now you change the experiment by putting the CCD camera here in the overlap between the two beams, then you get the pattern that Serge already showed. So I will gain time in not showing again, but the pattern that Serge showed was exactly that scheme that we have here. Okay, so this would be well, I cannot resist to show it anyway. No, okay, I resist. Okay, so we have wave particle here we have wave-like particle. I do it again. We have wave-like behavior for a single particle. Okay. Now, we also did the famous Wheeler's-Delitzsch experiment with the same source in collaboration with Jean-François Roch and his team and Philippe Grangy. Okay, so I claim that this is about the first quantum revolution. Planck, Einstein, Bohr, de Broglie, and then finally Schrödinger, Heisenberg, and Dirac, establishing a consistent formalism for quantization and allowing us, I wouldn't say to understand, but at least to describe faithfully this wave-particle duality. It was first conceptual, but we know that it was translated, as Serge emphasized, it was translated into technology. After allowing us to understand the structure of matter, understanding exotic properties such superfluidity, supraconductivity, etc., it gave a real technological revolution because it allowed physicists and then engineers to develop laser, transistor, integrated circuit, and there would be no information society if it was not for all these advances, which are the fruits of this first quantum revolution based on wave-particle duality. Now, as we already heard, there was this famous Bohr-Einstein debate in 1935, and from this debate emerged the importance of the concept of entanglement, and to that point probably it was not clear. Of course it was in the equations, but from this debate progressively it became clear that entanglement is an important concept. And so there was these experiments with entangled photons and the development of modern quantum technology. So in a few words, what was the EPR paper? This is a cartoon that I draw sometime. Einstein thought that that there are states in which two particles have strong correlation at a distance. And Einstein thought that if you have two systems which are so strongly correlated, for instance, you have measured one property here, I'm sure that the other partner has the same property. I take another property, and the other partner has the same value for that property. He said, how can we understand strong correlation at a distance? The simplest way to understand strong correlation at a distance is to accept the idea that from the beginning, the two partners have the same property. The best, I think, example we can give of that is twin brother. you have two twin brothers. They are born together, but because of life, one lives in Australia and the other one lives in America, okay? But when they are 20 years old, they have the same color of eyes, and maybe they will develop the same disease. And this can be understood because from the beginning, they had the same set of chromosomes. This was the idea of Einstein, Podolsky, and Rosen. Because of this strong correlation and distance, you have to admit that the quantum particles have this property from the beginning. This, of course, Bohr disagreed with that. Why did Bohr disagree? Because Bohr had the strong, I would say, intuition, because he did not demonstrate it, but a strong intuition that quantum mechanics, as he has elaborated it, was a consistent theory, and if you add anything to it, there will be self-contradiction in the theory. He did not demonstrate it, but he had the deep conviction of that, and he tried to elaborate this reasoning. But it was, so Schrödinger also understood immediately the importance and the intriguing character of entanglement, because he, immediately after the EPR paper, he wrote a paper starting with the following statement, which is very strong. This paper does not aim at the solution of the paradox, it rather adds to it if possible. Schrödinger realized immediately that entanglement is something extremely important. And then Bell, finally, I think, give the real demonstration of what Bohr had guessed, that is to say, if you accept to complete quantum mechanics according to the idea of Einstein, then there is a self-contradiction in quantum mechanics, and this is a famous violation of Bell's inequality. Okay. So there were all these experiments that some of you know, the pioneers, John Clauser, and then Ed was changed while the photons were flying between the source and the polarizer. So the way in which the photons are prepared here cannot depend on the following measurement that will be done here. It's the kind of daily choice experiment according to this kind of scheme that Wheeler has also developed on different circumstances. And so I would say that this experiment in which you change the orientation of the polarizer while the photons are in flight really put the emphasis on the contradiction between the ideas of Einstein based on relativity and the so-called local realism, which is a combination of the idea that there is a physical reality and that this physical reality must obey relativity, and conflict with quantum mechanics. So in a sense, it puts the emphasis on what some people call non-locality of quantum mechanics. And then after that, there is all the modern experiments. In these experiments, in the experiment of Clauser and in my experiment, the pair, it's a connection to my talk of this morning. The pair of photons were producing by atomic cascade, and the photons were emitted in any direction in space. With the new experiments, where the pair are produced by the nonlinear effect, the photons are produced in well-defined direction, so they could be fed into, for instance, optical fiber to do experimental test of Bell's inequality at a long distance. Nicolas Gisin in Geneva makes experiment where the distance between the source and the detector is several tens of kilometers because he's using the commercial network of Swiss Telecom. Okay, so all this progress. So the point which was discovered by Feynman as early as 1982 is that entanglement, being a new feature, should be good for something. And he invented the idea of quantum simulation, and then there have been more proposal and realization of what is part of quantum technology, so quantum simulation and calculation, quantum cryptography, quantum teleportation, etc. All these wonders of quantum technologies, which are based, as I said, on, as I said this morning, on entanglement, but also on observation and control of individual quantum objects. So this was my conclusion of this morning. So this is more global because it covers a full century. Okay, and with this, I think is, so we can discuss and, about that and disagree. Thank you very much.
So thank you, Alain, for this presentation. Now, I think, I don't know we can proceed, but I am sure that all the participants have different ideas which can go in the same direction of your presentation or can criticize your presentation. And also from the public here, maybe some can, it will be to have a discussion which would be a real discussion with some contradiction or so on. Okay, maybe Boris, do you want to comment something?
From my point of view, I totally agree with Professor Aspet, but maybe I born in a different century. I was from in a new trend. I think that young physicists think that the quantum objects, the quantum state, is objective. It's objective. It's objective. The quantum because in the old discussions, the quantum state appears like information or appears like some kind of representation of the world, but clearly for me and for another colleagues, the quantum state exists in the world. Is the real truth of the world. I don't know, it's a strong point of view, but I agree totally with your your points, but maybe in that, yeah, I am going beyond, of course, because for me, the quantum state, it's not different of or electric field or a position vector. And see that.
What do you mean when you say that the quantum state is objective? If I give you one particle within a given quantum state, you will be able to find what it is?
Yeah, of course. Because we can make a tomography experiment.
But for a tomography, you need many
copies. We need many.
So it's a statistical concept.
Okay. Okay.
So then we agree. If I give you one copy, you will not be able to tell which one it is, and this it is connected to the no-cloning theorem. If I give you one copy, you cannot make a lot of copies of this particle. What I want to stress is that quantum physics, and I think Alain said it at the beginning, quoting Bohr, is a consistent theory which is a build up and completely consistent, and if you try to change a little bit of it, the whole thing collapses. For instance, entanglement is a direct consequence of the superposition principle and the fact that the system made of many parts is represented in a Hilbert space, which is a tensor product. So you can make, once you have said that, plus superposition, entanglement is the direct consequence. On the other hand, if you want to give up the fact that the result of a measurement is random, you come to contradictions. You can communicate faster than light, and there is a lot of things which become possible. I am amazed at the fact that the theory is fully consistent and you cannot change it. Another point which I find also interesting, I think Einstein knew from the beginning that this entanglement was not violating relativity because you cannot communicate information faster than light. But I find it strange because it is based on non-relativistic Schrödinger equation, and still this is compatible with causality. And in fact, I think Gisin has shown that if you could clone particle with a fidelity bigger than 5/6, then you could communicate faster than light. And 5/6 is the limit, the limit that the no-cloning theorem gives to this. So I find there are still some things which I find personally mysterious about the beauty of quantum physics, even non-relativistic quantum physics.
I would like to elaborate on what you say. I must say that I am almost, I agree with you in the following sense. I cannot live
without thinking that physical reality exists. I need to have a physical reality. What I know from the violation of Bell's inequality is that this physical reality cannot be local. In other words, what we know from the violation of Bell's inequality is that local realism is incompatible with quantum mechanics. At this point, should we reject reality or realism? I think that the question is not really a good question because the two notions are really linked. I mean, what does it mean to have a physical reality for something here? Here means, in my mind, in space-time, okay? It's not only space, space-time. What does it mean to speak of the physical reality of something which is here if the world is non-local, that is to say something changing there, immediately changes the physical reality which is here. So I fully agree that it's a little, it's not so nice to try to say I abandon locality or I abandon reality. Anyway, personally, I don't ask anybody to follow me, but personally, I need images for my imagination, and once I think about something with this imagination, then I do the standard calculation as everybody, I use a standard formalism. And in my personal images, I do exactly what you do. That is to say, for me, the state as a kind of reality, and I know that I have to admit non-locality between the states. That is to say, if I do something here, then the state changes immediately and things like that. I can live with it. I don't ask anybody to follow me, but it helps me to have ideas, okay? So, well, about the point that how is it that starting from Schrödinger non-relativistic theory, we have this kind of things? It seems that Schrödinger understood almost immediately that when he tried to apply his formalism, exactly as you say, to two particles. When he was using only one particle, he developed a model, a kind of hydrodynamic model where you have a current of probability and everything is consistent. As soon as he tried to apply the Schrödinger equation to two particles, so in this tensor space product, he found that although nothing is non-local in the Hilbert space, as soon as you try to describe it in the ordinary space, then there is something which appears to be non-local and he immediately abandoned his interpretation. So, I mean, so as you say, people were aware of what was happening.
No, as long as you say personally, I think I cannot say anything.
I don't try to convince anybody.
No, but I think what you said about hidden variables for non-local systems, I agree completely with that, but I think the same problem arises when you make any quantum measurement, even in a local system. The example I took in my talk of a box in which you have a non-defined number of photons, I think you are naturally driven to think that the photon number was there before the measurement and you just revealed it by the measurement. If you take this line of reasoning, you are completely at odds with the non-commutation variables and you get wrong results, even if it's not non-local. You cannot consider that in a given system, the result of the measurement is hidden before you make it. It's non...
I fully agree, but there is something more in the entangled photon, it's non-locality. Because I know very well it's this discussion about this, there are some experiments, the contextual and non-contextual measurement. It amounts to saying that if I have a system and I measure first observable A and then observable B, it's not the same thing as measuring first observable B and then observable A. And in a sense, if we think of the interaction of the object with the measuring apparatus, Heisenberg microscope and something like that, it's not so surprising. What it is surprising is when the same non-contextuality is applied to two objects, one here and one there, because the interaction that I have here, of course, it's more difficult to understand that it can affect the other side. So I agree with you that the formalism is the same, but for me the main difference is that in the second case, non-locality comes into the game.
Maybe our vision of the reality is too distorted by our feelings of the things that we see. And when we need image about the quantum world, we need to abandon those naive images. We can we can stay thinking in the same way in the wave and the particle.
You see, it's not difficult to manage this kind of debate. It's so intensive to discuss. But I think it's time now to ask in the audience. Yes. Do you want to ask something or contribute?
I just want to make a question, actually two questions. So to Professor Harosh, at the end of your talk, you mentioned your experiments with cat states, yeah? And in your experiment in 2007, you said the size of the cat state was 2.5 photons, more or less. And at the end, you mentioned that for the new kind of quantum cavities,
yes,
quantum QED, they are making it 100 photons, yes. Yeah? Then I'm curious because, I mean, following Surek's theory, you will expect that the decoherence times goes exponentially small with the size of the system. Yeah? Yes. So would you like to comment on how this scales actually? And the second question, directly related with this, maybe for the panelists. So you're talking about all the beauties that we have achieved recently and the future, how it looks, but there are a few big difficulties to take these technologies into place, like how it scales with the size of the system, which is related to the coherence. So would you mind, I mean, the whole panel to comment on this talk? Thank you.
I can answer about the cat problem. When you prepare a state superposition, there are two times which are important. The time it takes to prepare the system and the time it will take for the system to decohere. Of course, if the time it takes to prepare the system is longer than the time it takes to decohere, it means that you will never prepare a state superposition. You will have a mixture even before. It's what happens with a real cat. If you try to kill a cat, it will take a time which is much longer than the decoherence time of the big system the cat is made of. But so in our experiments, if you increase the number of photons, it will take more time to create the system, to separate the two components, and it will take a shorter time for the system to decohere. And so that's the point where the border is. In our system, it's about 10 photons. We build CAT system with about 10 photons. Now with superconducting qubits, they can go up to 100 photons because the time it takes to prepare the system goes faster because of the larger electric dipole. And they made a lot of improvement about the decoherence time of the cavity damping time. So there is no strict limit. I don't know how big the system could be, maybe a few hundred photons, but at some point we will come to a boundary. The second problem that you mentioned, the fact that if you try to scale up system made of gates, you get in trouble with decoherence is true, but you have ways to try to get around that, like quantum error corrections, and maybe also, I'm sure that other people here have, colleagues here have different views. I think that we are still very far from a system which could scale up to make interesting calculations based on algorithms. Now, the very promising thing is the quantum simulators that Alain was mentioning, because then you need only a few tens of particles that you control in an optical lattice or in an ion trap or in a network of Josephson junctions, and then you get to situations that you cannot solve by just solving a Schrödinger equation with 2 to the 30 or 2 to the 40 quantum states, and you can make the system and look what happens, and maybe you can learn interesting things. I am much more confident in this kind of quantum computer, analogic quantum computers than the digital one. But also, I am sure that there are some people who are more optimistic than I am about this issue.
just a comment about what you say. Maybe these people are not only more optimistic, but younger than us. Considering my age, in my group, I decided quantum simulation is okay, but quantum computer with quantum gate, I will be dead. Dave is a young guy.
I want to come to a practical question, if you do not mind. I am interrogate myself on the practical source for single photon, and nowadays. What are the more effective? And this question is also maybe for Guimaraes, who is not intervened. If there's a possibility that the quantum dots can be used as single photon emitters. Is that
They are.
Pardon, they are, effectively?
They are single photon emitters. And naturally, there's nothing surprising about that because, I mean, they are like atoms. So if you put an electron there, it has a certain energy. If you put a second electron, which the maximum you can do in the same level, so the energy is different. So if you look at the same frequency, you always get just one photon at a time at that frequency.
That is a practical...
Single photon sources are a reality.
But it is controlled electrically.
The difficulty is to have a single photon on demand. I mean, you have to have a single photon emitted when you want it to be emitted. But that's as Professor Alan Speck just showed. I mean, this has a lot of...
It is what you showed also this morning when you presented the light going on the beam splitter and showing that there is a 0 at 0. It is a proof that it is a single photon.
Yeah, there's a single photon. But what you really need is a single photon on demand, isn't it? You have to trigger a single photon emission.
Oh, okay. Oh. There is another microphone, please.
Hello, sorry.
Yes.
Thank you. Okay, I was thinking about something Professor Rodriguez mentioned in his talk. He was saying that polarization was something classic, but that somehow is also quantum. Well, I was a little confused about that statement because we could polarize classical waves, mechanical waves, I mean. And I'm not sure what we mean about, or what we mean with polarization when we are talking about one photon, one single photon. My understanding, of course it could be wrong, is that when we are talking about a bunch of photons, it's much easier to make the analogy with a wave, and then we understand the concept of polarization because we have an oscillating field. But when we are talking about one single photon, well, there is no oscillating field there. It is the quantum of field. It's the quantum of energy in the mode of field. So I would like to hear from professors, especially from Professor Aspect, maybe in simple words about this analogy. Well, in my understanding, it is an analogy, but maybe something else between polarization, when we talk about waves, and single photon spin, which is a quantum feature of quantum objects, spin. So probably I think they are not the same, but we can pass from wave language to particle language, going from polarization to a spin. But I would like to check if that is okay, or I would like to hear you about that.
Okay. Yes, I think that the reason why Boris is right is that first is using single photons, okay? What is single photon? A single photon is the first excitation of a mode of the classical electromagnetic field. So when you define the mode of the classical electromagnetic field, you are still in the classical world, you have Maxwell equation, and you look for solution of Maxwell equation. So you take an elementary solution, which is a mode, and now this mode evolves like an harmonic oscillator. You quantize this harmonic oscillator, and the first level of excitation of that harmonic oscillator is the photon. So the first reason why he's right is that he's using one photon. I think that the second reason, so why is this classical property polarization suddenly behaving a quantum role? I think that it is because nature gives us polarizers, I mean birefringent crystals, which are such that when I send a single photon on it, I can only, and it has a given orientation, which is set by a parameter, you can get only two possible output results, dichotomic measurement. The intriguing quantum effects, you get them when you have single particles, or pairs of particles, but pairs well distinguished from each other, plus dichotomic measurement. For instance, if you think of Bell's inequality and violation of Bell's inequality, each time people come and tell you, oh, I have a classical system and you know I can violate Bell's inequality and something like that, the mistake is that they consider a value which does not give rise to a dichotomic measurement. So I think that what is really quantum in a system is a reunion of single particle and a dichotomic measurement. And we are blessed with the fact that we are given crystals, or we can build artificial polarizer, but there are systems which give a dichotomic measurement without, we don't have to think of it. Even if we don't know quantum mechanics, if we send a single photon on a crystal, it will go either in the ordinary array or in the extraordinary array, like a Stern-Gerlach.
Thank you very much, Alain Aspect. I think there is a problem here now, that we have limited on the time. Maybe you still have something to tell, but I am very sorry because we have to free the room now for another event. Yes, okay? So I want to thank all the so brilliant panelists. You see, the difficulty is not to begin the discussion, is to stop it. So, but you see, oh, of course, I know that.